What's specific quote?
We've talked quite a bit, we've done a lot of problems about static and kinetic friction. We talked about anti-lock brakes, right? So we're gonna go back to some car stuff today. If we look at our friction equation, so let's just look at kinetic frictional force, if you're trying to stop in a hurry on the road. Kinetic friction or static friction, same model. Right? Is that dependent on velocity? No, not at all. It only depends on normal force and the coefficient, right? So that's kind of a problem in a way. It'd be nice if it were proportional to velocity. That would be helpful to us, wouldn't it? Because it would allow us to stop quicker in a car, right? But it's not. So, and we're going to find out later on that the deck's even stacked against you worse than that, because you would assume then that your stopping distance would be proportional to your velocity, and we'll show here, within a couple of weeks, we'll show that, no, it's actually not. Your stopping distance, unfortunately, is not proportional to velocity. It's worse than that. Your stopping distance increases non-linearly with velocity, which makes cars are dangerous. So that's unfortunate. Okay, now let's look at a different type of friction. So we've looked at surface-to-surface friction, but obviously there are other kinds of frictional forces that aren't technically, wouldn't even call them friction, but they act in much the same way. So give me an example. Well, what's another impeding force that you would experience other than just surface to surface?
Air resistance.
Air resistance, okay? Air resistance, it's a lot of times it's not a big deal for us in our everyday lives, although it can be. I mean, it can be. If you're playing badminton, it is, right? When you play badminton, what happens if you try to smash the...
Slows down.
It slows down in a hurry, doesn't it? I mean, it goes pretty fast for a little bit, but then it pretty quickly gets to its terminal velocity and slows down, right? What's that? Water, okay, definitely water. You dive in the water, it slows you down a lot. In fact, if you get too high, it's downright scary to jump into the water. If you get really too high, it's downright deadly, right? It's a pretty powerful force. So that's a different type of a force, though, than surface-to-surface friction. In fact, we don't really even call it friction; we call it drag. Let's think about this. Let's use your everyday experiences, and let's see if we can kind of come together with rudimentary theory of how drag must work, and then we'll fill in the dots and we'll fill in the blanks, and we'll give you an equation here in a second. So describe drag. What are some things you know about drag? You've experienced it when you dive into a pool. You've experienced it when you stick your hand out the window of a car. What do you know?
It grows exponentially the faster you go.
Okay, so it definitely is velocity dependent. Right, and you can prove that to yourself very easily. If you let your hand go through the water very slowly, do you feel any drag?
No.
Nothing appreciable. But if you try to really push your hand through the water, you feel a lot of drag. Right, so definitely, clearly, it's velocity dependent. Yeah.
Increase the surface area more.
Okay, increase the surface area, you're going to get more too. Sure. So the bigger the surface area, the more, and we got to be careful about that. So I'll give you an example. What if we took, for example, do I have that basketball in here? I don't think I do. You can visualize this though. So if we took let's take a circular flat plate with a radius of 1 meter, and let's take a sphere with a radius of 1 meter. If I'm going to drop those through the air, let's say, or let's say I'm going to attach them to some kind of a rod that's going to push them through the air. Okay, and we're pushing the circle through the air, so it's perpendicular to the direction of the air traveling by it, right? So that makes sense. It's catching the air, so to speak. It's going like this. Okay. Which one do you think is going to have experience more air resistance? The sphere or the flat one? The flat plate. Okay, the flat plate definitely experiences more, even though its surface area is actually smaller than the sphere, right? So it's actually not the surface area we're concerned about. It has to do with the shape, and it has to do with the cross-sectional area. So just the part that's actually facing the fluid that it's traveling through. Okay, so right, and so there's a word we know, aerodynamics, right? So we want to, if we want to create an object that's going to cut through the air with minimal drag, you basically know what the shape's going to be. It's going to be kind of long and streamlined, right? And there's some other things, there's some other ways that we can impact that to our advantage too, other than just making it streamlined. But in general, something that's long and streamlined is going to be more aerodynamic than something that's really blunt, right? Everybody agree? Okay. So we're kind of getting an idea here then. It's definitely velocity dependent. It has to do with, for sure it has to do with the shape of the thing, right? So we're going to have to assign some kind of a number to that, to the shape. And this isn't necessarily, this is not the kind of physics where we can sit down and really probably just calculate what that number is going to be. Typically, these are numbers that are calculated in wind tunnels. And we'll just create a list of all these different shapes. And we'll look to see what, how the shape impacts the amount of drag, and we'll quantify that in terms of a coefficient. Just going to be a number that we're going to multiply by our drag that's going to be associated with the shape. Streamlined, lower number, smaller drag. Blunt, larger number, more drag. Yeah.
A golf ball as opposed to a rounded object.
Okay, now that's interesting. Yeah, there's weird stuff going on. I'm glad you brought that up. So sometimes bizarre little things that we would not have predicted make a difference. Like, you know the story about a golf ball. Golf balls used to be perfectly smooth, right? Back in the day. Golf's been around forever. Back in the day, golf balls were made, not using so much high-tech materials, but still they were made round, same size, but smooth. So turns out that if you put dimples on the surface of a golf ball, it goes a lot further. And it has to do with the way the air interacts with the surface. So it really does change what we're going to call the drag coefficient, which is the shape of the object has an impact on how well it cuts through the air, right? Streamlined, easier, blunt, less easy. Dimples, it turns out, make something more streamlined in a way, even though it doesn't really change the macroscopic shape of the thing. Those little dimples, they have an impact. And it's pretty complicated the way it works. Question? The texture definitely makes a big difference. What's an example of that? Like when you watch the Olympics, and you're watching swimming, what do you notice?
No hair.
Yeah, okay, no hair, sure. True. But you hardly can even tell because they're all now wearing these high-tech suits. And what's the purpose of that suit? Yeah, it slips through the water, right? So the material on the surface has very little resistance with the water, and so that also has a big impact on the drag coefficient, is what it's made of, right, for sure. Okay, so with these golf balls, so there's an interesting story. How did that get discovered? That's exactly it. Yeah, the old, garbage golf balls that were all scarred up were going further than the new ones. And so what's that telling you? That when you score the surface and you create all these little crevices on the surface, it had some impact. And then when people kind of seized on that idea and said, well, what if we do this a little more scientifically? And they dimpled the surfaces and they found the patterns experimentally that worked the best. And so there's a lot of tech that goes into that stuff. Okay, so let's see if we can get this though. So if we're trying to do drag, let's see if we can kind of build our equation here. Drag is going to depend on, we said, on shape, right? Streamline versus blunt. What else? You said area, right? Cross-sectional area. So the area that's actually seeing the fluid that it's traveling through, right? We don't care, like for example, if I were to take like this meter stick and I threw it like this, and I compared that to just a little chunk of wood that had the same cross-sectional area, is the extra length going to really affect the aerodynamics much? No, it actually makes it better, honestly. It makes it better, not worse. So really all we're concerned about is just that little bit that you're seeing, coming at you, that's cutting through the wind. That's the cross-sectional area. So that's the part, you can think about it as the part facing the fluid. Okay, what else? What are some other dramatic examples of where drag would be increased? Like if you're when you dive off of the high dive at the pool, how many fluids are you traveling through? Two. What are they?
Water and air.
Water and air. Okay, which one obviously has a much higher drag?
Water.
Yeah, the drag force of the water is much bigger. How come?
Because there's more
There's
molecules.
more molecules per.
Okay, there's more molecules per, so what's that probably? Parts per million. Okay, you guys are flirting with it here. What's the
Volume.
well, what is it? Density. There we go. Yeah, density. Good. The density of the fluid is going to make a difference. And if we want to get a really sophisticated model, there's some other things going on too. I mean, it's the viscosity would be another issue. But usually, when we're talking about, we got to make a distinction. There's a, what's the rule called? Somebody's law. I can't remember off the top of my head what it is. But you kind of divide drag into two camps, and there's a gray area in between. But if you've got a relatively dense object moving through a fluid that's not very dense, then we call that drag. But if you have a relatively light or small particle or object traveling through a viscous or dense fluid, then it acts completely differently. It doesn't act, what we're going to come up with here doesn't apply at all. It's totally different. And that's why you could, if you're a mouse, you're essentially indestructible. I haven't heard those words before. If you're a mouse, I mean, you could drop a mouse out of an airplane and the mouse is going to live. You could drop it down a mine shaft and it's going to survive. But if you took a rat and dropped a rat down a mine shaft, unless it's a really tough rat, it's probably going to die. And if you drop a person, that's no good. They're going to be broken. If you drop an elephant, it's just going to splash, right? I mean, so there's a dependence here. How come the mouse survives? And they do.
Because they're not very dense.
Okay. Okay, so there's a ratio here that's going on. So to a mouse, air is relatively more viscous than it is for us. You can think of it that way, right? If an object is really light and or small and it's traveling through a fluid that is, it's reasonably viscous, then it ceases to follow this model that we're going to be talking about, and it follows a different model which doesn't have this huge dependence on velocity. Like if you were to take, for example, you could see this if I were to, I don't have any probably chalk on this. There's no chalk in here anywhere, but if you took like in an old school room, if you took two erasers and you smashed them together, you'd get a suspension of little particles of chalk dust. If we were to shine a light on that, what would you notice about those particles? Are they going to fall rapidly to the ground? No, they're going to float around for a long time, right? Eventually, they'll probably make their way down to the ground, but we might have to leave for an hour and come back before they were on the ground. Any little people just walking around the room, the air currents would spread them around, right? How come? Because they're not very dense and they're very tiny, and so they see the air as being much thicker, more viscous than we do, right? Same thing with bugs. Well, say it again. What's that? What? Oh, yeah. So mice are going to be somewhere, they're down closer to bugs than they are to people, right? Mice are small enough that if they fall, their terminal velocities are really small. They're not going to be that high.
So surface area is
Surface area is relatively big. And if you get something like a flying squirrel, then it's taking something that's already pretty small, and it adds some extra, just has some webbing on its, essentially like little webbing that connects its elbows, like a parachute kind of. And they can go, they can travel almost horizontally. Have you ever seen a flying squirrel jump? They go a long ways. How come? Well, because they're pretty small. The air is pretty thick to them, and they've increased their drag coefficient substantially by even getting bigger. Yeah.
So you could throw the flying squirrel out of an airplane and it might be able to actually stick landing.
Yeah.
It would be going pretty fast.
Okay, but I don't think so. I think a flying squirrel probably hits terminal velocity when it jumps out of a tree.
Oh yeah.
I don't think it's gonna make any difference if it's falling out of an airplane or if it's falling off the roof. Yeah, they kind of hit their terminal speed and that's that. So, and obviously you could drop a spider or an ant from, it's not gonna hurt it. Anywhere, right? So you can see things change. Okay, so.
But elephants.
So those, would you agree those are probably the three ingredients? Oh, and obviously
Yeah,
velocity, we already said velocity, right? Yeah. It's a little bit of a myth. They don't always, but they usually are pretty good, and that has to do with conservation of angular momentum. And we will talk about that soon. We'll actually take that exact example and we'll, if you watch a cat, here's my short answer for now. I don't want to tell you too much. But if you ever watch a cat in slow motion when they're falling, they'll spin their tails. Yeah, they're very flexible, but they'll spin their tails too. So they're doing some good physics when they do that. And we'll get there
Cats are the
eventually.
real physicists.
No, go back.
Go back, sure. Actually, everything that's on there is going to be better on the next page anyway. Okay, so then we've got drag force. So we know that we already told me that drag force is proportional to velocity. It turns out it's proportional to velocity squared. So try this, little everyday physics. Try this sometime when you're on like a place where you have access to freeway and surface streets. Try putting your hand out the window of the car when someone else is driving. And it'd be better if you could even do something like maybe have like a ping pong paddle. Hold that out the car. Just
You're
try
not gonna be
this.
able to hold on to it.
Well, I mean, it wouldn't be that big a deal. But hold it while you're going 10 miles an hour, 20 miles an hour, 40 miles, no, not 100, 40 miles an hour, and maybe for short duration get up to 80, so so we're gonna double it. I want you to see what happens. So I want you to see what happens with that. When you double the speed, initially you're not gonna notice it as much because they're pretty small, but when you go from 10 to 20, it's not just linear. I mean, you're gonna notice that it actually increases, it's gonna be as the square of the speed. So when you go from 20 to 40, but 40 to 80, you're gonna, by that point, the forces are big enough that you can really tell. That's not linear. I mean, they're really getting pretty strong. Okay. So
Have you
just,
ever put pennies on your fingers?
what do you do?
You put little pennies on your fingers.
Oh, and hold them out the window?
Yeah.
Oh, that's kind of cool. I never thought about that. Huh. Well, that's good.
Paper.
That's good.
Until you actually look
Eventually,
at it.
yeah. Well, no, so when you slow down, they fall off though.
Yeah.
Yep. That's good. That's a good way to do it. I never thought of that. So here's the equation, right? Here's our drag equation. Is it exact? No, it's not exact, but it fits pretty well. For most normal velocities that we would deal with, this works pretty well. So drag force equals 1/2 times c times rho times av squared. So what are those things? Well, c is the drag coefficient. That's going to be much like a coefficient of friction. It's going to be something you're going to have to look up in a table. It's not something you're just going to know or be able to calculate. It's something that's been measured in a wind tunnel, and there are lists that are just published.
And that's gonna be the shape of the.
Yeah, it has to do with the shape, right? The shape and the texture and things like that. So then we've got, in addition to that, we've got rho, which is the fluid density. So for air, that's going to be really small. For water, that's going to be pretty large. Okay? Obviously, that's going to contribute linearly, right? So the bigger the fluid density, the greater the drag force, right? If I double the density, I double the drag force. Same thing with drag coefficient. And it's a coefficient, so that's going to be unitless, right? That's just a number, just like a coefficient of friction. A is the cross-sectional area, so that's going to be the part facing the fluid. Okay, so for example, if you were going to, let's say we were looking at a bullet going through the air. What's going to be the cross-sectional shape? Circle. Everybody agree? So if I were just to cut through that thing where it's impacting the air, that's going to be the cross-sectional area. Okay?
But can you look at that in 3 dimensions?
Say that again?
Wouldn't you look at, I know, but wouldn't you look at that in 3 dimensions?
Meaning, I think you're saying something pretty good here. Say more. Articulate that a little more.
I mean, if you looked at a bullet with a flat face, it would have
Right,
the
okay,
same.
that's what I thought you were saying. So like if you look at the profile of the bullet now, not in cross-section, the bullet kind of looks like this, right? Whoops.
Yeah.
Kind of looks like this. Is what you're saying. It's not just flat, it's actually got a taper at the end.
Yeah.
Right, and so, you're right, and so what do? Is it truly the cross-sectional area? Well, not really. There's a lot of fudging going on with this. You're gonna have to say, okay, well, where's the critical place where you're gonna measure it? And there's a whole bunch of physics we're not talking about. I mean, there's a lot. There's a lot of things that go into this. This is a much simplified, much simpler version of what drag force would actually be if you're calculating it using calculus, differential equations or something. And then there would be all kinds of, like there'd be a Reynolds number, it's another kind of an index that's built from the shape. How do you characterize the shape? Is it characterized as a truncated cone? Is it what they call it, a bilaminate cone with a sphere, hemispherical? I mean, all kinds of different shapes you can match this to. And they're all, what's the length of the thing compared to the cross-sectional area? All of this stuff goes into a more sophisticated model, which uses all these other numbers, like Reynolds numbers and Mach numbers, how many times the speed of sound are you going. There's all kinds of other stuff that go into it. But that's getting pretty sophisticated. So what we're going to do is we're just going to say there's going to be some cross-sectional area which is going to be essentially the front of this thing. But if it's cutting down to to just a pinpoint, well then that's really not the cross-sectional area because it's flaring out. So somewhere along that taper we're going to say, okay, that's the average radius, and so that's going to be the cross-sectional area. So it's not like it's just cut and dried though. Yeah. You're right, we're fudging it a little bit with this simplified version. But this is honestly, it's what most people would use most of the time. Yep.
Does the speed of sound change with fluid density?
It does, yeah. Generally, the speed of sound goes up as the fluid gets denser.
Because the molecules are closer together.
Yeah. Yeah, so, okay, so then what about cross-sectional area? Okay, so that's it, right? And I told you that there were, like we could look at, there's a lot of different ways of determining drag coefficient, and part of it is, I just pulled this out of a textbook somewhere. This just gives you kind of a rough rule of thumb. Once again, it's not a firm, hard, fast rule here, but generally a sphere is going to have a drag coefficient about like that, plus or minus a little bit. Half sphere is going to be, a little different. Cones are a little different. Oddly enough, spheres have less drag than cones do.
Where are we,
What's that?
for which way is the air is coming to?
It's coming direction of the arrows.
Oh, okay.
So a streamlined body like that, I mean, look at that. When you start to have something that's kind of a teardrop shape, look how low the coefficients get, right? And so you'll notice that when you look at a lot of like futuristic cars, when people are looking at cars of the future that are trying to really streamline stuff, a long time ago people used to think that, well, all you gotta do is make them pointy. Well, you really don't. You wanna make them more like this, right? You wanna make them more streamlined. And having what's called a ducktail on the end, like this, helps. It really does. It seems like it's just extra surface area, but if it tapers and it's longer in the back and tapers, that actually improves the drag coefficient. Yeah.
What's that little bitty looking symbol thing up above?
Let's see.
The proportional to symbol.
Oh, yeah, right there. Sorry, yeah, that's I forgot to say that. That's proportionality, right? And so this is in general too. Drag force, in generally true, drag force is roughly proportional to v squared, but if we want to come up with the actual equation, then we have to include all this other information, okay, all these other factors. Okay, and so we can look at it this way. We can look at kind of by shape, or we could even, did I include a little list here? Yeah, like we can look at cars. These are just measured in wind tunnels. If you look at these production cars, oddly enough, look at the Camry, it's really low. And there's a lot of good engineering there. 0.28, compare that to, like a Ferrari Testarossa. That's a little older Ferrari, but that's 0.37. I mean, that's quite a bit higher, which is odd.
Where can you find them?
What's that?
Yeah. Where can you find those?
Oh, just on Google.
Why
Like
is
if you
this-
just Google the cars with the lowest drag coefficients, you're going to find a lot of pretty sporty cars. Although sometimes these cars like this, like Testarossas, sometimes they're actually going to have a little bit higher drag coefficients because they've got spoilers. So there's two things going on. They're trying to cut through the wind, but they're also trying to increase their surface-to-surface friction by increasing the normal force. So they'll sometimes have spoilers and little foils that push the car down. It actually hampers, it hurts the drag coefficient a little bit.
Why is the feet per skydiver so high?
Is a feet first?
Shouldn't that be lower than like a truck?
No, not really, because why would that be? Why would a skydiver be higher, substantially higher than a car?
Because less mass.
Okay, but the mass isn't really the issue here. It's not really mass, but think about what about a skydiver would not be nearly as good as a car.
It's not uniform.
Driving.
Well, it's not uniform. Okay, sort of. Think about the kinds of materials. A car is made of a rigid, very dense surface, right? Not a skydiver. Skydiver's got clothes that are flapping around, right? You're carrying a big backpack on your back. I mean, there's a lot of stuff that's, right, you get that? If you wanted to travel to Alaska on vacation and you were going to carry a bunch of luggage with you with a car top carrier and you wanted to maximize your fuel economy, would you have a hard shell luggage rack or would you have one where you just kind of, that's open where you just strap canvas over the top or something? Hard shell, for sure. There's a lot of, and we'll look at this from a different perspective later.
Is it also because
And we'll look at this from an energy perspective. And anytime something like if you have flaps on your car like a canvas, you'll hear that the whole way, right? That's energy, right? There's sound energy being produced. When that thing flaps around, there's a lot of energy that's required to make that thing flap around. And where's that coming from? Well, coming from the car.
would it also be part of the air going through the canvas? Would that
Yeah,
have
but
an
part of
effect?
it's the material. It's a porous material instead of a slippery material. I mean, you can do things like coat something in Teflon. If you coated this Civic in Teflon, which wouldn't be a good idea, that would go down because Teflon is slippery. Okay. Okay, so let's look at something then. Let's take an example. Let's just calculate. How about something that's kind of fun to do? Let's just calculate. How about what the terminal velocity is for skydivers going feet first or horizontally? We'll just take a normal person. Okay. First of all, how could we come up with an equation, a really good equation here for terminal velocity, starting with this. So let's do it on this page. What could we do here? Now this is a force, right? This is the force produced by the fluid that's acting on the body traveling through it, right?
That,
So if you're at terminal velocity, what simple equation would we have to come up with then?
The mg minus
that.
drag force.
Okay, so then we could draw a free body diagram. If this is the person falling, right, then we've got, what are the forces acting on the person
Gravity.
falling?
Gravity.
Okay, so there's their weight
And then
pulling down
drag,
and drag force
that's it.
pushing up, right? And eventually, at first the drag force is really small, right? Because they're accelerated. But as they pick up speed, what's happening to the drag force? It grows and grows and grows, and eventually it matches the weight, and that's when you hit terminal velocity, so the net force is zero. So this is a pretty simple equation, right? Equation of motion here vertically is just drag force minus mg equals zero, right? So then if we want to come up with an equation for terminal velocity, we'll just start by setting, if we add mg to this side, we know drag force would equal the weight at terminal velocity, right? So our equation is just going to be this, right? Okay, so all we got to do is solve for v, right? V is, and that's going to be our terminal velocity when drag force equals weight. So that's nothing. We're going to multiply both sides by 2, right? We'll solve for v squared first. Multiply both sides by 2, so we're going to get a 2 on the top over here, and everything else is just going to get divided to the bottom. And then to solve for v, I would just square root it, right? So there is a formula for terminal velocity. Okay, what's it depend on? Now notice this time mass is included also, right? So being more massive, is that generally going to help or hurt you if you're trying to go faster? It's going to help you, yeah, right? It's going to help you. Okay, and things that are going to slow you down. If your drag coefficient increases, obviously that's going to lower your terminal velocity because that's on the bottom of the fraction, right? If the density of the fluid gets bigger, that's going to slow you down. Or if your cross-sectional area gets bigger, that's going to slow you down. That all makes sense. So let's do a little calculation here. Let's just say for a person who is for me, how about, if I'm going skydiving and I'm going to fall horizontally, so there's the ground, what's my surface area? Be kind. So it's about, so it's, say, 2 meters by, we'll just kind of ballpark this by, and I'm gonna be kind here, by, I don't know, I don't know. So probably just say half a meter if you're wearing clothes that go down, down your legs and stuff, so right? What's that? Is that pretty kind? Let's see. That's half a meter, it'd be right about there. So on average, that's gonna be close enough, because I'm not quite 2 meters tall either, so. So we'll say our area, my area is, if it's 2 meters by half a meter, what is that? 1 square meter. Okay, close enough. Okay, mass. That's gonna be, what is that gonna be? A little less than, so what's 200 pounds in kilograms?
It's gonna be about 100.
It's gonna be a little less than that, like 90.
95.
We're closer to 90.
Isn't it .455 kilograms?
I don't know, it's 2.2 pounds. per kilo.
90.718.
There we go. Okay, so we'll just say 91. Okay, so we need the, we got that, don't we, from our list? The drag coefficient. That was on the list, right there, about 1. Okay, drag coefficient of about 1 for horizontal. Okay, so, oops. C is about 1. Density of air. So somebody Google this real quick. If we're skydiving, because actually temperature is going to make a little bit of a difference here. So let's say we want the density of air when the air is about, let's say 20 degrees Celsius.
The higher you up, the higher up you
The
are.
higher, the colder it'll be. Yeah. So we're doing this in the summer, but still 20 degrees would be. Is that hot? What is that going to be?
Wouldn't it be less dense up high too?
Yeah, it does get a little less dense with altitude too. What is that going to
Yeah,
be?
15, it's 1.225.
1.225. It's not going to vary that much, but so rho 1.225.
Yeah.
And then across it, we got area. I guess we got everything. Mass. Yeah, we got it all. Next point. This is actually kind of interesting too. It's the higher you get, the less dense the air is. In fact, some crazy guy set a record. He essentially skydived from the edge of the atmosphere. Remember hearing about this?
Oh,
I
yeah.
think it was a Japanese guy maybe that did
It
this.
was Red Bull. It wasn't him.
What's that?
It was a Red Bull guy. It wasn't him.
Oh, it was a Red Bull guy that did it? Okay. Okay. I'm thinking of the guy that skied down Everest. That was the Japanese skier. He didn't make it though. That was bad. Yeah. So the crazy Red Bull guy, probably too hopped up on Red Bull, he jumps out and he goes so fast because the air is not very dense up there that he actually breaks the speed of sound. So he was going, like over probably close to 800 miles an hour. So he was really cruising. And then as he got lower, the air got more dense and he slowed down. But initially he was going really fast. Actually broke the. Well, yeah, he made it, but I don't know. He had to have a suit on and everything, obviously, because he couldn't breathe up there. So what does this give us then? If we plug and chug here, what do we get? Square root, somebody do this, square root of, and use the little fraction template, 2 times 91 times 9.8 divided by 1 times 1 times, so divided by 1.225, what do you get?
38.16.
Okay, so that's about, we're gonna get about 38.2 meters per second. Let's convert that to miles per hour. So we get a sense, for us, that's probably a better way to compare.
That's really fast though.
It's pretty fast. I'm gonna guess that's probably gonna be, I would guess 110, 120-ish, something like that. Maybe a little more than
38 is 85.
That's it, 85 miles an hour? Wow. That's not very fast. Everybody else got the same answer, 38.2?
Yes.
Okay. Okay. Well, I guess if you're going like this, maybe. Now there's only one change we have to make if we want to compare that to feet first. So we're gonna reduce, so in that same calculation, we're just gonna change the C to a 0.7. What do we get?
Was the last one supposed to be when we were horizontal?
Yeah, that's horizontal.
So that's how fast you hit the ground?
Yeah. If you're horizontal.
45.6.
Point
I always thought you could survive.
0.607.
607. Okay, so what's that?
I got this.
You got what?
I got the same answer.
What'd you get?
46, 45.6.
Yeah. Okay. Okay, so what is that in miles per hour?
102.
102? Okay.
It's really fast.
So what's your strategy then? If you're ever in the unfortunate situation to be falling out of a plane without a
Go
parachute,
horizontal.
like what do you want to do?
Increase
Yeah,
your
you would. You seriously, you would.
Increase
You'd
your
want
stress
to.
area.
You'd want to like fan out your coat as much as you could. You'd want to fall for as long as you could horizontally, and then at the end, at the very end, you'd want to try to rotate and go vertically. Yeah, that's what you'd want to do. Like the last, right as you're getting down there, you want to. What's that? To maximize your chances of survival. And people have survived, parachutes not opening, falling out of planes. And we'll talk about this soon too.
Water or on?
They landed, no, not in water. Water's generally not good.
Yeah, that was thinking.
But there's other things that they could do, and we'll get to this pretty soon. So just to.
If you went sideways, wouldn't it help? Like, if you're horizontal but angled, so you're moving not straight down but at an angle, would that help? So the forces kind of disperse.
Could potentially help a little bit,
And then
yeah.
You can turn around.
Do they land in certain things?
What's that?
Do they land a certain way or?
Well, you'd want to land feet first, but that's quite a difference. You definitely would want to stay horizontal and try to make yourself as big as you could. Spread your arms and legs out and try to increase that drag coefficient, right?
Make a parachute.
Yeah. All right.
Make a parachute.
What are we out here, 10 minutes?
Yeah.
Oh,
We got 2 minutes.
okay.
Yeah.
All right, I've got an assignment I'll put up. What?